Hello, my name is Nathan Shauer, and I'll present work for my recently completed PhD at the University of Illinois, advised by Professor Armando Duarte. Guided waves that propagate along fluid field fractures are commonly called Crowley's waves. These waves are known to be highly dispersive because of the elastic media that bounds it. The focus of this work is to develop a computational method for the three-dimensional simulation of such waves. Crowley's waves have applications in numerous fields where fractures cannot be directly assessed, as in fractures around volcanoes or glacial crevices, also in the oil industry for hydraulic fracture treatments. The governing equations for such waves are in the solid medium, the elastic waves, and for the fluid flow inside of the fracture, a compressible Navier-Stokes description with lubrication theory. The fracture solid is then discretized in space with the GFEM and in time with the average acceleration Newmark beta method. And the fluid flow inside of the fracture is discretized in space with the standard FEM and in time with the alpha method. The final system is monolithically solved for displacements and fluid pressures and velocities as shown here. The final system is symmetric and linear and can be factorized and assembled only once if the time step does not change. First, here the problem with manufacturer solution is analyzed, where optimal convergence rates were obtained for all three fields in the L2 norm. In here, a verification problem is analyzed, where the solution fields can be seen in this figure, and the phase velocity with respect to frequency is compared between GFEM and analytical solutions for 4 different initial openings with great agreement between them. In this section here, a validation problem is presented where once again the phase velocity with respect to frequency is compared between experiments and GFEM with great agreement between the quantities. And lastly, here at the right, a 3D elliptical fracture is analyzed to test the robustness of the method, where complex fields for the pressure and opening are obtained. I would like to conclude saying that we developed a stable 3D GFEM methodology to robustly and accurately solve Crowley's waves that is verified and validated. And the GFEM can actually capture opening variation near the front and is ideal for inverse problems since the mesh does not need to fit the fracture surface. Thank you for your attention.